Hello and welcome. In this video, we're going to take a look at the division of polynomials, which is kind of like how we would divide integers in a way. If you're taking two whole numbers and you have a dividend divided by some divisor, we might try using long division. It might be something you haven't done for a while. You're kind of used to just doing division on a calculator. Now, a calculator is going to get you a decimal. It's going to get you some decimal representation of that division. But if you think back to long division, you try to get the divisor into the dividend, and you do that by going sort of one digit over at a time until you finish it up. And if it doesn't go in evenly, you just call it done. There's a remainder. Now, it's going to be the similar process here when we're looking at division of polynomials. We're going to have a remainder. And maybe before we dive into that, we should just remember what are the common properties about a polynomial. There's a couple things that we should probably make sure that we're familiar with. First of all, when we're talking about a polynomial, we talk about its degree. And if a polynomial has degree n, that means its highest power of x is going to be x to the n. That would be this first term here. And so every of these little underlined pieces separated by addition, these are called terms. And this one in the front here with the highest power is called the leading term. It's the one that has the highest power, x to the n. Of course, we're assuming here that the leading coefficient is non-zero. Now, we talk about the division algorithm. It's the process by which we do division, and then we can express some sort of quotient here with a remainder. The division algorithm states that if we have a polynomial p of x, and that will be our dividend, and d of x, which is going to be our divisor, as long as the divisor is not 0, then when we divide p of x by d of x, there should exist some unique polynomial q of x, which we call the quotient, and r of x, the remainder, that satisfies this equation. P divided by d equals q plus the remainder r over d. Now that could be rearranged. Oftentimes, the division algorithm is written as the polynomial p is equal to the quotient times the divisor plus some remainder. And it makes it a little bit easier to see, but we're going to be needing really the fractional form here, so that when we divide some polynomial by another, then we might be able to state that as a polynomial plus a remainder over d. Now let's take a look at the division that we have to perform here. It's going to be just like long division. Now in this example, I've got the dividend, 4x cubed plus 3x squared minus 5x minus 6, divided by the divisor, x squared minus 1. I'm going to start off by writing this in our typical long division form, x squared minus 1 into 4x cubed plus 3x squared minus 5x minus 6. And it's important to make sure that all of the terms go from highest power to lowest power. And if any of the coefficients are 0, it's actually quite helpful just to write a 0x or a 0x squared somewhere in there if necessary, just so that you can see x cubes, x squareds, x's, and constants. You can basically see all of the different terms. Now, we focus just on the leading term here, x squared, and the leading term, 4x cubed. We see how many times x squared divides into 4x cubed. We can write that down. 4x cubed divided by x squared. 4 divided by 1 is just going to be 4, and x cubed divided by x squared is simply x. And you can double check. X squared times 4x is 4x cubed. That 4x is going to become part of our quotient. We'll write that above, where the quotient is going to end up. And just like long division, we have to then multiply the divisor by that quotient. So 4x times x squared minus 1. And when you distribute, we will have 4x cubed. We'll write that below. Minus 4x. And that's going to have to go in the column of x's. We'll subtract to see how much remains. 4x cubed minus 4x cubed, we'll see that they have canceled out and there's no x cubed. 3x squared minus 0x squared here, well, subtracting from 3x squared, nothing. We just end up with 3x squared. And watch out for subtracting a negative. Negative 5x minus 4x is going to really be adding. So that's going to be adding 4 minus 1x. Now we're starting this process over again. But this time, the leading term, x squared, is going into the leading term, 3x squared. Of course, we can bring the 6 down as well now. So we're really dividing into a new polynomial. We're dividing x squared minus 1 into a quadratic now, whereas we started off with a cubic. We're getting closer to the end now, because we're dividing a quadratic into a quadratic. Leading terms, once more, 3x squared divided by x squared is just going to be 3. And that's going to be our last column here, is the constants column. 3 times x squared and 3 times minus 1, making sure they go in the correct columns, and then we subtract. 3x squared minus 3x squared is 0, and then negative 1x minus nothing is negative 1x, and negative 6 minus negative 3 is minus 3. And you continue this process until you find out that the remainder has a degree that is smaller than the divisor. Seeing here that the degree of the remainder is 1 and the degree of the divisor is 2, we are done. So that means that the quotient here is 4x plus 3, and the remainder is negative x minus 3. And going back to the division algorithm, that means we can write it in one of these two forms. And to add to this division algorithm, the uniqueness of q and x is guaranteed as long as we have the degree, or just deg if we want for short, the degree of r of x must be less than, strictly less than the degree of our divisor d. Or of course, the remainder could be 0. Having completed the long division, now let's see how we can rewrite this rational expression. We can write 4x cubed plus 3x squared minus 5x minus 6, all divided by x squared minus 1, as being the quotient 4x plus 3 plus our remainder, negative x minus 3, all divided by the divisor, x squared minus 1. And you can see that this new fraction is a lot simpler than the original. It may also be worthwhile just to take that negative sign and move that out front. Now, the process of long division can be useful for several purposes. The long division will allow us to see a little bit of the behavior of the graph of this function. So you might see how this 4x plus 3, as being the quotient there, well, that's just a nice straight line, 4x plus 3, and that might help us to understand a little bit about the behavior of this function. It's going to have a little bit of a sort of a linear sort of behavior to it, but not necessarily everywhere. Another thing it's going to help us out with, much further down the line, is calculus, actually. Some of the operations that we want to perform on rational expressions are pretty complicated. It may be a lot easier if it's possible to express a rational function as much simpler ones. And here, it's not much simpler than 4x plus 3. We just end up with a much smaller fraction that we have to deal with. Now, another application that we can use immediately here is actually to help us find a way to factor polynomials with higher degree. We see that there's a way to know that if there's an x-intercept, some sort of root of a polynomial, if c is a root, then x minus c must be a factor. And if we know something is a factor, then when we divide, we should end up with a remainder of 0. Dividing by something that goes evenly into a polynomial, dividing by one of the factors of a polynomial, should give us a smaller degree polynomial that might be easier to factor than the rest of. So that gives us a good opportunity to use that right away. Now, especially on the note of dividing by a nice easy factor, like, so let's say, x minus c, a very easy linear factor, then there is another form of division that we can use. Whereas long division is very similar to long division of whole numbers, we have another method of division called synthetic division. Let's suppose that we have a polynomial, p of x, then that would be our dividend. And we want to divide by a linear polynomial x minus c, and that would be our divisor. Well, we could certainly use long division, but when we're doing long division, we're really kind of writing out a lot of unnecessary x's and x squareds and x cubes and other things. All of those extra little bits of information for something as simple as dividing by a linear polynomial, we can omit that and actually sort of do the same process, but with a shorthand notation. In this example, I've got a cubic polynomial divided by the linear polynomial x minus 4. For our shorthand notation, whenever we have a linear polynomial of the form x minus c, we're just going to write that value of c on the left-hand side, in this case, 4. You can always think about this as just being x minus 4 equal to 0 and solving for x. That's going to be on the left-hand side. And then the coefficients of the polynomial we'll write just to the right of that. And the coefficients need to go from highest power to lowest power, and we can't skip any powers. If there's a coefficient of 0, it must be written down. So starting off with x cubed, we have the coefficient 3. X squared, the next term down, has a coefficient of 0. The x linear term, that has a coefficient of -2. And then the constant term has a coefficient, or just the constant 7. Now, when we're doing division, usually we do a long division symbol here. Synthetic division has a similar looking symbol, except that we're going to be working our way down. Now make sure to leave an extra little space here for the room that we would normally take up by doing all of the small little steps of long division. Now think about long division. If we have 3x cubed divided by x, then we know that x is going to go in 3x squared times. And that 3 is really the important part of knowing what the coefficients of the quotient are going to be. And so we always know that the first coefficient of the quotient, 3 divided by 1, is just going to be 3. And so really just think about this 3 here is going to become the leading coefficient of our quotient. Now, because it's a linear term and we're going to be multiplying x minus 4 all by 3 in long division and then subtracting, we're going to get this minus 12. And that's what we're going to be doing here as well. Take the 3, multiply that by 4, and we'll end up with 12. Of course, in long division, we would be subtracting -12. And here we have simply just addition straight down, 0 plus 12. That's going to give us the next coefficient of our quotient. So as we go down the columns here, we can think about this as simply being addition. And the very first column we can just think of as 3 plus 0 is 3. And now we have 0 plus 4 times 3, which is 12, gives us 12. And we'll continue this process. 12 times 4, and that'll be 48. And then -2 plus 48 is 46. Now we can continue onward, add down, multiply by 4, 46 times 4, and then 7 plus 184. Now, just think about what happens when you divide a cubic by a linear. A degree of 3 divided by a polynomial of degree 1, well, it should end up with a degree of 2. And if you have a quadratic, then we can have an x squared term, an x term, and a constant. So what are these 4 numbers down here? The last number here is actually not the quotient, but it is the remainder. And so, at last column there, we can see we'll end up with a remainder. R of x is just simply equal to 191. The degree of that polynomial is 0. And so, of course, we're done because the degree of the remainder needs to be less than the degree of the divisor, which is degree 1. The 3 numbers here, well, because we've been shortcutting this with synthetic division and we haven't been writing down x's and x squareds and whatnot, we're going to have to remember how to organize these terms. 3 here is really just the x squared term. 12 represents the x term, and 46 would just be the constant. And so we've got the quotient, the remainder, and we can state the division algorithm. And there we have it. We've got now a cubic divided by a linear is just going to give us a quadratic plus some remainder over that linear x minus 4. Now let's just compare that to what this would look like with long division. And I'll leave it to you. If you want to, you could skip ahead in this video. But Maybe if you don't understand why synthetic division works, you might want to watch this little bit here on long division so you can just kind of see the shortcuts. Well, setting up the long division here, we'll just have to make sure we write the coefficient of the x squared term in the dividend as being the coefficient 0. We'll start by looking at how many times x goes into 3x cubed, which is going to be 3x squared. And so you can see that's really what we're doing here. We're just going to get that 3 right away. And then when we're subtracting, we're going to have to take 3x squared times 3x minus 4. And that gives us 3x cubed minus 12x squared. And we always know that these first leading terms are going to cancel. Really, the only thing we have to look at is 0 minus negative 12. That's going to be just like adding 12. So we end up with 12x squared. And that's the same process that we're doing here in synthetic. Because we're not using minus 4, we're just using plus 4. We've switched the sign. That means we're just adding 0 plus 12, whereas in long division, it's 0 minus negative 12. Same idea, though. And then we'll bring down this 2. And of course, we can bring down the 7 while we're at it. Leading terms, once more, we're just going to see how many times x goes into 12x squared. But of course, that's just going to be 12x. And that is simply just what we end up with here in green. Whatever we added down, 0 plus 12 is 12. That's going to be exactly how many times the leading term goes into the new leading term. We're really shortcutting that process by using synthetic division. With long division, we still have to write out 12x times x minus 4. And then we have to remember that we're subtracting, and subtracting a negative is really just adding. Oh, and whoops, I've just seen that I've actually written down plus 2x when I should have had negative. Correct that. There we go. Negative 2x minus negative 48x is 46x. Same number that we get when we're just doing negative 2 plus 48 over here. We'll bring down that 7. 7 minus 0 is simply 7. And then we end up with, well, 46x divided by x is just 46. You can see that's going to be the last term in our quotient now. We still have to do the rest of the work for long division, though. 46x minus 184. And then when we subtract, we'll get that remainder. We're doing all the same processes in synthetic division, but realizing that because linear divisors are just much more simple, then synthetic division takes care of the whole process for us. It's just going to be adding straight down and multiplying diagonally. And there we have it. There's our two main methods of division. Remember to really only use synthetic division if you're dividing by x minus c. Otherwise, stick with long division. And long division will always work anyways. Synthetic division is simply just a shorthand way to divide by x minus c. And we'll see in a future video there, if you divide by x minus c and you get a remainder of 0, that's great. You've just taken p divided by d and you've turned it into a single polynomial, which means that you've actually just been able to pull a factor out of a polynomial. And factoring something with a degree of 3 or higher is something that's pretty challenging. You know, maybe we'll look at a way of how to predict factors. If they are in fact factors, then we can divide them and we'll be able to factor higher degree polynomials that way. But we'll leave that for later. Thanks for watching, and I'll see you in the next video.